Okay, so maybe we can start with the concluding talk of today. It's a plenary talk by David Conlon, who is one of the leading experts in Ramsey theory, extremal combinatorics, additive combinatorics, and among other things. It's a pleasure that David agreed to talk on our conference. And yeah, so then we'll talk about Sparse algorithm as well. Thanks for agreeing.
Okay, thanks for the introduction, Andre. Yeah, so I'm going to talk about a theme that I've been working on for quite a while, which connects to lots of different things. So it has connections to random graphs, to extremal graph theory, additive combinatorics, Ramsey theory as well. So the basic thing, the thing where I'm going to start and build the talk around, is the triangle removal lemma, which is this very classical result, essentially due to Rouge and Samredi. I'm not sure they were the first ones to state it in these terms, but certainly the origins of this goes back to a paper of Rouge and Samredi in the late 70s. And the statement is simple. So it says that any n vertex graph that has little o n cubed triangles can be made triangle free by deleting little o n squared edges. So if you have few triangles, you can get rid of all those triangles by deleting few edges. Okay, so this is a nice, simple result. It's actually based on, the proof of it is based on the regularity lemma, and I'll talk about that in a minute. But it looks quite simple. So at least to begin with, it looks like the kind of statement that you can just, if you tell somebody, they can just sit down and prove it straight away, just by, finding an edge that's in lots of triangles, throwing that away and seeing what happens. But that doesn't work. In fact, to date, there is no simple proof of the triangle removal lemma. Everything relies on regularity in one sense or another. And one of the reasons that sort of points to why it's difficult is that it has some nice applications. So for example, one application is that it implies the theorem of Roth from the 50s. So Roth proved it using Fourier analysis. But it has, again, quite a nice statement. It says that if you take a subset of 1 up to n that contains no 3-term arithmetic progression, then you have size little o of n. Or to go the opposite way, if you have delta n elements of 1 up to n, then you necessarily contain a 3-term progression, provided you're large enough. Okay, so this connection between what's happening in the graph setting and what's happening in the number theory setting sort of runs through the talk, and I'll touch upon this a few times. So I'll just say quite briefly what it is or how it is that this works. So the proof of this goes roughly like this. You don't really need to know the details particularly, but assume that A is a set that doesn't contain a 3-term arithmetic progression. Then using this set A, you can build a tripartite graph using that set A. So this big N it's comparable to N, to this little n that I had on the page before. But you put an edge between x and z if x minus z is an element of A, and similarly the whole way around. And the conditions that you give here, the reason that you give these conditions is that you get a triangle for each arithmetic progression. In fact, for each arithmetic progression, you get quite a few triangles. But on the other hand, we know this set A was chosen so that there are no non-trivial arithmetic progressions. So actually, the only triangles you get in the graph are the ones that come from trivial progressions, where the 3 elements A, B, and C are all the same. So you do get that this graph contains triangles, and in fact, you can show that the constructed graph is it's a union of edge disjoint triangles. Okay, so if it's an union of edge disjoint triangles, then for one thing, we know that there are actually few triangles. There's at most n squared triangles. So there's at most n squared triangles. That means you can apply the triangle removal lemma to actually remove all of those triangles. And you can do that using delta. You can remove delta n squared edges to remove all of the triangles. But because every edge is actually contained in a triangle, that actually means that the number of triangles or the number of edges to begin with was at most 3 times delta n squared. So actually it bootstraps itself and tells you that the number of edges if it's at most n squared, it has to be at most delta n squared, and then that actually goes backwards to imply that the set A we started with has size at most delta n. But the point to take out of this is that there's a way to take this set A, to encode it as a graph, to then use the triangle removal lemma, and then bring it back to get the conclusion about the original set A. Probably this is the most technical thing I'll say in the whole talk, by the way. So, but I don't know why I put it on slide 2. But basically, this exact idea, or relations, relatives of this exact idea, are used later on. Okay. So this removal lemma actually has lots of different applications and lots of things that are more or less equivalent to it. So here's one. There's a standard extremal function in extremal graph theory where you let FNVE be the largest number of edges in a 3 uniform hypergraph. So the edges have size 3, where there's no collection of V vertices containing E edges, which takes a little bit of getting your head around. So one of the standard cases is this. It's the Rouget-Samoredy theorem. This is what they originally proved, and it's essentially equivalent to the triangle removal lemma. And the statement is that if you have a 3 uniform hypergraph such that there's no collection of 6 vertices containing 3 edges inside them, then actually the number of edges in the graph is little o n squared. So if you're close to n squared, then you're guaranteed to get 3 edges on at most 6 vertices, or bunched up in some way. An equivalent version of this is actually, this is completely equivalent, is that a 3 uniform hypergraph on n vertices with girth larger than 3 has little o n squared edges. Now, girth for hypergraphs is a little bit subtle. So for one thing, girth greater than 3 suggests you have no triangles of edges. That's true. But you also have to factor in that it has no cycle of length 2. And that just means that any 2 edges share at most 1 vertex. They're not allowed to share 2 vertices. Otherwise, you can sort of think of it as being a cycle of length 2. Okay, so these things are equivalent and all nice applications. They're fairly equivalent to the triangle removal, not exactly equivalent. Okay, and as I said earlier, the proof of this removal lemma and the proof of all of these things has 2 ingredients. So the first ingredient is the classical regularity lemma of Samoredy, which he proved when proving Samoredy's theorem. So Samoredy's theorem is the generalization of Roth's theorem to k-term arithmetic progressions. So it says that if you have delta n elements of 1 up to n, then provided n is large enough, your set will actually contain k-term arithmetic progressions. So this arose in the middle of that proof, and the statement basically is that you can take any graph, you can chop that graph into a bounded number of parts in such a way that most of the pairs of parts, the graph between them is actually random-like in a certain way. Usually it's referred to as epsilon regularity, but basically the edges between them are nicely randomly distributed. But on its own, the regularity lemma is a lovely statement, but it's not all that useful. Usually it's paired with something called a counting lemma or an embedding lemma. And these counting lemmas that I want to talk about today. So in the particular case of triangles, the counting lemma, it has the statement that so if I have 3 pieces, a tripartite graph like I was talking about before, in fact, like this. So I have 3 pieces and I have 3 vertex sets like this, and each of these is random-like. So it has some positive density and it's random-like. Then actually the number of triangles that you get between these 3 pieces is close to what it would be if each of these was random. So if the densities of these were alpha, beta, and gamma, and the size of each of the sets was n, then you'd get around alpha times beta times gamma n cubed triangles. So it would be essentially what you'd expect in a random graph, up to the epsilon that comes into the random-like. So if you're familiar with regularity, this is all completely obvious. But so by combining these 2, essentially, or variants of this, is essentially how the regularity lemma is always applied. So in the version, when you're applying it and trying to prove the removal lemma, the way in which one does it is okay, so you have your partition of your graph, and what you do is you go through and you throw away all the edges between pieces that aren't regular. So for example, if this wasn't regular here, then I just throw away all the edges there. If the number of edges is too small as well, I also just throw it away. Okay, so if that happens, and at the end, I'm still left with a triangle like this XYZ, then that actually tells us that the three pieces, so the big X containing this little x, and the big Y containing this little y, then the vertex or the edge set between them must be dense and it must be regular. Otherwise, it would have been removed and thrown away. So all three of these pieces, just the fact that there's a single triangle there implies that these are actually all dense and all regular. And then that actually tells us that in actuality, we have a lot of triangles. So we just apply the counting lemma, and the counting lemma tells us that between big X, big Y, and big Z, there's loads of triangles, which contradicts our original assumption. And that's essentially how the removal lemma goes. And again, what we do later revolves around doing similar things in slightly different contexts. Okay, so what is it that I actually want to talk about? I said I was going to talk about sparse counting lemmas rather than just counting lemmas. So what do I mean by a sparse graph? So regularity classically applies to dense graphs. And by dense graphs, we mean graphs that have n squared vertices, or sorry, around n squared edges, like delta n squared edges, something in that range. But what I'm going to be interested in is what happens if it's polynomially smaller than that. So for example, what happens if the number of edges is n to the 3/2 instead of n squared? Can we actually say anything in that regime about regularity? And the answer is no. So it's actually fairly straightforward. So first, the regularity lemma breaks down in the sparse setting. That's somewhat fixable. But then it turns out that even in the sparse setting, even if you know that your three pieces are regular like this, you still can't guarantee a counting lemma. So you could end up in a situation where you have a sparse graph, you know that the three pieces are regular, and even then you can't count the number of triangles. So you need to do something more if you're going to make progress. And the standard assumption, or the standard way to do this, is we make an additional assumption, and that additional assumption is that we're working with subgraphs of very nicely behaved graphs. So the graphs that we're interested in are themselves contained in other graphs that are really well behaved, such as random graphs, usually binomial random graphs, or pseudorandom graphs. And within those contexts, we can do something. So for example, a regularity lemma in the sparse context is actually it's fairly easy to prove. You follow the usual proof of the regularity lemma, and you just need to put in one extra condition, which is that no subgraph is too dense. So there's never a spot within your graph that is much denser than the average density. And it turns out if that's true, then everything goes through. But counting them is a totally different story. So actually coming up with appropriate counting lemmas, or ways in which these counting lemmas work, is significantly harder. So until quite recently, the thing that was studied the most is what happens in random graphs. So can one recover a counting lemma with respect to random graphs? And here, about 10 years ago, there was a huge surge in work in this area, to the point where we now really understand this quite well. So what we know is that if we have a random graph, then we can do counting within subgraphs of a random graph of appropriate density. So for example, if we're interested in counting triangles, then if we take binomial random graphs, so each edge is chosen independently with probability p, where the density is larger than around 1/√n, then within that context, if you fix such a random graph, then with high probability, any subgraph of that random graph satisfies a counting lemma. So you can sort of do regularity with respect to subgraphs of that graph. This is part of, I mean, I haven't even given all the names here. So there's a huge amount of work that went on whereby you could transfer, essentially you could take your favorite combinatorial theorem, no matter what it is, and transfer it over to the random setting, provided it was about some bounded object. So for example, if you had a theorem about triangles, so a good example is Ramsey's theorem, for example. So then you can say that Ramsey's theorem still holds within random graphs of small density. So if you take a random graph of density C divided by square root n, then Ramsey's theorem still holds in there. So if you color it in two colors, there will always be monochromatic triangles. But the same is true. You can do it for Turan's theorem. You can do a random version of Samorati's theorem. You can do a random version of the removal lemma. So just to give an example, this particular theorem goes back to work of Hayakawa, Wyczak, and Rödel, who stated a very important conjecture in this area that was only eventually solved by Balog, Morris, Samity, and Saxton and Thomason. But here's a typical consequence. So essentially, for any epsilon, there exists some delta and some c, such that if your probability is at least c divided by root n, then with high probability, a triangle removal lemma holds within GNP. So every subgraph of that copy of GNP, which contains at most delta times the total number of triangles, so delta times p cubed n cubed, can be made triangle free by removing at most epsilon times the total number of edges. So it's the same statement, but just relative to GNP. It's saying that if a subgraph has a small portion of the triangles, then you can make a triangle free by removing a small portion of the edges. And this is a typical statement. So this was generalized. So the removal generalizes from triangles to all possible graphs H, fixed graphs H, and a similar thing happens here. So there's a result of myself and Tim Gowers, who first generalized this so that it holds in all graphs, or with respect to all possible H instead of triangles. But this whole area could easily take up a talk by itself. But I just wanted to point to the fact that for random graphs, things are pretty well understood now. Yeah. Okay. So that's one area. Another area is what happens for pseudorandom graphs. Within pseudorandom graphs, and actually pseudorandom hypergraphs, and all of the random stuff extends to hypergraphs as well, we actually do have a counting lemma in this context. This is a more recent result. So the random results from about 10 years ago. This is from maybe 6 years ago. And I'll say on the next page a little bit about what I mean by pseudorandomness, but in general, by pseudorandomness, I mean that it has some of the properties of random graphs, but you're already given it deterministically. One of the reasons why the random thing works is because you have the union bound, which isn't something that's available in pseudorandom graphs. Okay, but a typical consequence of this is this. So it turns out that, again, because you can relate graphs to sets of integers, that you can prove a pseudorandom version of Samorati's theorem. So Samorati's theorem is the statement that dense subsets of the integers contain arbitrarily long arithmetic progressions. And this is saying that if you take a subset A of the integers, which is sufficiently pseudorandom in some sense, then that set will be Samorati, in the sense that any subset A prime of that set A with positive relative density with respect to A also contains arbitrarily long arithmetic progressions. So Samorati's theorem is just the case where A is itself everything, but it still holds for pseudorandom subsets. And one nice consequence of this is that this relative Samorati theorem actually gives a different proof of the Green-Tau theorem. So the Green-Tau theorem is the statement that the primes contain arbitrarily long arithmetic progressions. And it turns out that this purely graph theoretic statement is the main ingredient that's needed to prove that. So in some sense, we give an alternative proof with the Green-Tau theorem. And what's actually happening here is that, so Green and Tau prove a statement like this as well, but the statement that they prove has a stronger pseudorandomness assumption. So their pseudorandomness has two different aspects, one called the linear forms condition and the other called the correlation condition. And our work shows that this correlation condition is not actually necessary. As a result, it's simplified actually a lot of things that have come out of the Green-Tau theorem, and our result has been applied, for example, to get the asymptotics for polynomial progressions in the primes. Okay, but again, I sort of wanted to wave at this as I went by. But let me say a little bit more, for this you need hypergraphs. Let me say a little bit more concretely about what one does in the graph setting. So in the graph setting, there's a very concrete notion of pseudorandomness, and that concrete notion is what are called ND lambda graphs. And ND lambda graphs are graphs which have n vertices, where the degree of each vertex in the graph is at most d, and all of the non-trivial eigenvalues are small, so they're less than some lambda. And lambda could be as small as something like the square root of d. So in very pseudorandom graphs, lambda is the smallest square root of d. When I say non-trivial, I just mean there's always a trivial eigenvalue where you take everything to be 1, and then you get d to be the eigenvalue. And in this context, actually, let me quote a result of somebody else. So the result is a result of Kohayakawa, Rödel, Schacht, and Skokan, who prove a triangle removal lemma in this context. And again, it's very similar. So there you have some technical conditions. The technical condition is that your lambda is sufficiently small. So it should be less than p cubed n, where p is the density. Then if that's true, if your ND lambda graph satisfies this technical condition, which measures the pseudorandomness, then triangle removal holds. So again, if you have a delta proportion of the triangles, you can make it triangle free by removing an epsilon portion of the edges. And this was generalized. So the work by myself and Jacob Fox and Yufei Zhao generalizes this to all H again. So and much more besides. So essentially, you're in a situation where you can do the same thing that I talked about in random graphs, where you can take any combinatorial theorem about some fixed graph or fixed structure and then transfer it over to a sparse setting. Okay. Partly I mentioned this because there's actually a very nice open problem here, which is that the condition here that lambda be less than or equal to p cubed n might be improvable to p squared n. So in the random case, all of the results are optimal, essentially. But here for pseudorandomness, even for triangles, the results aren't necessarily optimal. One thing we know is that this condition, this p squared n condition, is enough to guarantee the appearance of triangles. And in fact, it's tight. There's a beautiful construction of Noga-Alon showing that, that this is the best possible condition. And essentially what it's saying is that there are optimally pseudo-random graphs of density n to the minus a third, which is actually much higher than what you get in random graphs. But the question is this condition that guarantees that you contain triangles, is it enough to guarantee that you have a rich collection of triangles, rich enough that you can actually guarantee that the removal lemma holds? And this we don't know. So there's a very nice recent result of Patrick Morris, for example, showing that, again, at this threshold, you get a triangle factor. You get a collection of triangles that cover all of the vertices of your graph. But we don't know if there's enough to guarantee that the triangle removal holds, for example. Okay. But let me move on to what I actually, I want to talk about something relatively new, which is recent work, again, with Jacob Fox and Yufei Zhao, but also with Benny Sudakov, where we develop sparse regularity, in particular sparse counting, for graphs that contain few 4 cycles. Now, this is quite different to what happened before. So previously, assuming that you're contained in a random graph is quite a strong condition. Assuming you're contained in a pseudorandom graph is also a pretty strong condition. Just assuming that your graph has few 4 cycles isn't that strong a condition. It's actually substantially weaker. It can still be seen in the same terms because a graph with few 4 cycles or no 4 cycles is implicitly contained in a maximal graph with no 4 cycles. And and you can see that that has to be pseudorandom in a certain sense. So in some sense, it's a weak pseudorandomness condition, assuming that you have few 4 cycles. But because that pseudorandomness gets sort of compactified into this statement that you have few 4 cycles or no 4 cycles, it actually gives lots of nice corollaries. The main result, in some sense, is that if we have a graph that contains few C4s, few 4 cycles, then there is a counting lemma for 5 cycles. So assuming that you have no 4 cycles, you can actually count 5 cycles. And I'll focus, rather than focusing specifically on how we prove this, I'm going to focus on the corollaries of this. So for one thing, you might expect that counting lemmas tend to apply removal lemmas, and that is true. So one of the main results is that if you have a C4 free graph on n vertices with, the statement looks slightly arbitrary, but I'll explain in a minute why it's not, with little o n to the 5/2 5 cycles, it can be made 5 cycle free by deleting little o n to the 3/2 edges. And the reason why that is, in some sense, the correct statement is that the largest possible C4 free graph has density around 1/√n. So the natural density you're working with is p is equal to n to the -1/2. And so if you write p is equal to n to the -1/2, then the statement is that for any epsilon there exists a delta, such that any C4 free graph on n vertices with at most delta times the proportion of possible 5 cycles can be made 5 cycle free by removing at most epsilon times the number of edges. So again, you're in a situation where you're basically getting a relative removal lemma that if you have less than a delta proportion of the 5 cycles, you can make it 5 cycle free by removing at most an epsilon proportion of the edges. Okay, so this is actually the natural statement, and there are several other variants of this statement. This one is less obvious in some way. So any graph on n vertices with little o n squared 5 cycles, so this is a stronger condition, can be made triangle free. So this is again stronger. So instead of deleting 5 cycles, we're actually deleting all triangles by deleting little o n to the 3/2 edges. So again, this is a little o of the proportion of all possible edges. But the condition here that we need is stronger in order to guarantee triangle freeness. And we know that this condition, this n to the 5/2 condition, is too weak for this to hold. Okay, so we get this these nice relative removal lemmas if we assume that we're C4 free, but we also get a bunch of very natural statements. So the first, if we recall, so earlier we had this statement that FNVE is the largest number of edges in a 3 uniform hypergraph where no V vertices contain E edges. Then one thing that's actually equivalent to our first removal lemma, so the first one here, is this statement. So if we don't want there to be 10 vertices containing 5 edges, then we have little o of n to the 3/2 edges. It's not so hard to get some constant times n to the 3/2 as an upper bound here, but this is saying that like the Ruggier-Semeredi theorem, you can actually get a little o statement. And to draw a better analogy, this statement is completely equivalent to the statement that if you have a 3 uniform hypergraph on n vertices whose girth is larger than 5, then that has little o n to the 3/2 edges. So again, you're banning 2 cycles. 2 cycles being the situation where you have 2 edges sharing 2 vertices. You're banning triangles, you're banning C4s, and you're banning C5s, or 5 cycles of these 3 uniform edges. But assuming all of that, it turns out that the number of edges is little o n to the 3/2. There's something strange that we don't understand here, actually. So it turns out as the girth goes up, what seems to be happening is, so you can have girth 2 and you can have n squared edges. You can have a bunch of triangles that are edge disjoint, essentially. That's no problem. It's a design or a Steiner system, essentially. If you go to girth at least 3, then it drops to little o n squared. If you go to girth 4, it drops to n to the 3/2. So girth greater than 4 drops to n to the 3/2. 5, you're getting a little o n to the 3/2. And we know that for 6, it then drops again to n to the 4/3, but for 7, we don't. I'll return to this at the very end. but we don't know how to extend this result to girth greater than 7. So it should be that there's an equivalent result saying that for girth greater than 7, you have little o of n to the 4/3 edges, but we don't know how to prove that. And I'll say at the end why we don't know how to prove that. But this is a nice natural statement that comes out of this and extends Ruja-Samarady in a very natural way. But one of the things that actually really makes this interesting is the number theory applications. So here's a typical example of a number theory application. So let's fix some integers, a and b. Then the statement is that if 1 up to n, so this n is just a shorthand for 1 up to n, has no non-trivial solution to this equation. So ax1 plus ax2 plus bx3 is ax4 plus a plus b times x5. Then the set actually has size little o of square root n. And again, the reason this is interesting is that there's a very easy way of showing that this is at most square root n. Basically some Cauchy-Schwarz type argument. So getting it down to this little o root n is actually interesting. It shows that there are very simple equations where there's some non-trivial thing happening. So I've given an example here where this holds. So it holds for this particular equation. I should also note that we don't know that this is sharp. So it may be that actually in this particular case that the true answer is polynomially smaller than square root n. This is actually reminiscent of something that happens at around size n as well. So it's known that the equation, so 3-term progressions are encapsulated in the equation x plus y equals 2z. And we know that if you want to avoid solutions of that, you need to have size little o of root n. So this is in some sense an analog of that at square root n. But at n, there's equations like, for example, there's the equation 2x plus 2y is equal to z plus 3w. And for that equation, we know that the solutions, again, you need to have size little o of root n, little o of n to avoid solutions. But it might be the case that there's a polynomial improvement for that particular equation. And that's an old question of Ruja that we really don't know anything about. And it's possible that something similar is happening here, actually, that beyond this little o of root n, you're actually getting a stronger improvement. Where that doesn't happen is for this result. So this is a similar kind of result. Again, we have a 5-variable equation. All of these results extend to things with more than 5 variables as well, but 5 is the minimum we can do it for. So you have a 5-variable equation. The simplest version is just this. So you take x1 plus x2 plus x3 plus x4 is equal to 4x5. Assume that you have no solutions to that equation, but also assume that you're CDON. So what does CDON mean? CDON means that you have no solution to x plus y is equal to z plus w. This is a standard thing in the area. And what this is saying is that if you're a CDON set, so you have no solution to x plus y is equal to z plus w, and you have no solution to this nice translation invariant equation, then actually in order to avoid both of them, you need to have size little o of square root n. And there we know that this is essentially sharp. So up to some e to the root log n factor. Okay. I should note this was also after we proved it. Sean Prendeville, who works in additive combinatorics, found quite a nice proof just using Fourier methods that also proved this. Okay. Now the reason this is interesting is because of the following. So we're simultaneously avoiding solutions to 2 equations. The first is the CDON equation that x1 plus x2 is equal to x3 plus x4. And the second is solutions to this simple translation invariant equation. Now, it turns out that there are CDON sets, so avoiding copies of this first thing, of size square root n. In fact, we know the constant, essentially, it's 1. So there are subsets of 1 up to n of size square root n with no solutions to this thing. And this second equation, there are sets of size close to n, so n to the 1 minus little o1, which don't contain solutions to this. So for both of them on their own, you can avoid solutions at square root n. It's not really a problem to avoid solutions to the 2 of them at square root of n, but if you're trying to to either of them rather. But if you're trying to avoid solutions to both of them, it turns out that's not possible. So, to avoid solutions of both, you have to actually drop to little o of square root n. And that's interesting. In fact, this is the first time anybody's uncovered this phenomenon for linear equations. So it's related. So there's a conjecture in graph theory that if you take a collection of graphs, then the extremal number of that collection of graphs should basically be the extremal number of the minimum, or the minimum of the extremal numbers of the graphs. That's not known to be false. It is known to be false for 3 uniform hypergraphs, but this shows that it's also false for linear equations. And I suspect that it is also false for graphs, but it seems considerably more difficult to disprove for graphs. But somehow this disproves it for linear equations. Anyway, so we actually wrote 2 papers about this. So the first paper was this one, which basically just had C5 counting and all of these applications. But we came back for another bite recently because we were interested in the question of, so if we know that our graph is C4 free, which graphs can we actually count within this? So we know that we can count C5s. And there are several necessary conditions. So, well, there's a couple of necessary conditions. One is that if you're going to be able to count a graph within C4 free graphs, then you have to know that the girth is at least 5. There's something called a polarity graph, which is a very large C4 free graph with around n to the 3/2 edges. And you can modify that graph slightly and show that versions of that graph don't contain C3s or C4s, or counting fails within these modified polarity graphs. So that's one thing that we do actually know. The other thing that we don't actually know, but we think is true because of analogies with random graphs, we think that it must be the case that any subgraph of your graph has to be sparse, essentially. So the heuristic that we have is that any subgraph H prime of your graph H has to have at most twice the number of vertices minus 4 edges. So in particular, that actually tells us that any such graph, if it's regular, any countable graph has to have degree less than 3. So it's not possible, if this is true, it's not possible to have 4 regular graphs that are countable. Okay. So these 2 things together rule out quite a lot of graphs, but in the other direction, the main thing that came out of our recent paper is that you can count graphs within C4 free graphs if the graph H has what we call an islands and bridges decomposition. And again, I won't define this completely rigorously, but I will try and at least point to what it is or how it is that this works. So here's an example. This is C5. This is the first thing I mentioned. So we know that these C5s are countable. So what are the islands and what are the bridges? The islands are the things contained inside these purple bits. So these are our islands. And the condition on these islands is that the graphs induced inside of these islands have to be countable. So a single vertex is countable, an edge is countable. That's not particularly hard. All right. The bridges are these connections between them. So connecting one vertex of one of the islands to another vertex of another island is a graph sort of between them. And the condition on these is also that they should be countable. They also need to satisfy another condition that we call tameness, but I'll not worry too much about it. So what's actually happening, the reason this works is that if you take the 2 endpoints and you sort of double the bridge around those 2 endpoints, you get a C4. And that C4 is tame in the sense we're interested in. But I'll not dwell too much on it. So basically the islands and the bridges need to be countable, and then there needs to be an extra technical condition on these bridges. But the bridges, for example, paths of length at least 2 always work as bridges. Okay. This, by the way, also sort of shows why it is that we're able to count C5s. So the reason, and this is oversimplifying massively, is that if I fix a vertex here, then that vertex has a degree around square root n. So the number of vertices at distance 2 from that original vertex is actually square root n times square root n. So it's around linear. So each vertex actually has around linearly many vertices at distance 2. To actually guarantee that, you need to use the C4 free condition. So as a result, this thing, if I forget about the intermediate edge, has a sort of 2 neighborhood of linear size, and we can use regularity to show that there still have to be edges inside of that neighborhood. That is a gross simplification, but essentially that is the idea of what's happening behind this. Okay, so this is the first example. This also works very easily for longer cycles because, so for example, for longer odd cycles, I could just put, for longer cycles in general, I could just put a path, say I'm looking for a 6 cycle, I could put a path of length 2 in here, and then I can connect the endpoints with bridges to the opposite side. So that gives counting for cycles. Here's a more complicated example. So I said already that what you need is you need your islands. These purple patches or lilac patches are islands. There's a 5 cycle in here, and there's a 5 cycle on the edge. And then I can connect those islands using these bridges. And each of the bridges I'm attaching hits the inside C5 and the outside C5 exactly once, and each one is just a path of length 2. And I could use paths of different lengths or paths of different types. But you get this nice sort of flower shape from just doing this. So this is countable. Here's a less obvious example. So here, again, we have 2 islands. So one island contains an edge, which is countable. Another island contains a vertex, which is countable. And then we have 2 bridges. So the first bridge is this 2-edge path here, which we know about. And the other bridge is this much larger thing. So actually, the thing that we're connecting as a bridge over here is just this graph as though we removed this bottom C5. But it turns out that this is countable and it satisfies this tameness condition that I was worried about. So you can actually glue using that. And you can iterate. So you can iterate this procedure and you can add another C5 here, and then you can add another, C5 down here, and you can basically draw a wall of these C5s. Was there a question there? All right, but this is not a classification. We don't know a classification. Classification seems kind of hard. And
David, I think now there is a question. Can there be more than 2 islands?
Yes, there can. So I know I've only used 2 islands, but yes, there can be more than 2 islands. So so it depends. So for example, the standard simple bridges that I use are just these paths of length 2, but there's no problem in, I could actually use this large thing here with another island over here if I wanted to. So yeah, you can use, there can be arbitrarily many islands. The key thing is that the bridges can only hit each island once on only one vertex. So, okay, so these cases are open. The one on the right is, sorry, the one on the left is an icosahedron, just sort of unfolded. So it's an icosahedral graph. The one on the right is the Peterson graph. Why are these interesting? So, well, they both have girth 5, so they satisfy the first condition. They also both satisfy this sparsity condition. In fact, each of them is 3 regular. So I already said that 4 regular, we really can't hope to count, but these 3 regular ones, it looks like it's at least plausible that we can count them, but we don't know how to do it. Somehow all of our procedures start at some point by using a path. And a path always has some vertex in the middle, which has degree 2. So we don't know how to do these. And these are interesting and they're open. And I'd like to see positive or negative answers to either of these. Okay. So to conclude, let me just again hark back to this thing I was mentioning about longer cycles. So the question is there a removal lemma for 7 cycles in graphs with few 6 cycles? So we've been assuming there's few 4 cycles and counting for 5 cycles. But it should be the case that if you ban 6 cycles, or have few 6 cycles, then actually you get counting for 7 cycles. It's a completely reasonable thing. And in fact, the counting aspect seems to be okay. It feels like if we try and follow the methods that we have for counting, it seems to go through in this case. It's slightly simpler if you take girth larger than 6 rather than no 6 cycles, but it goes through in much the same way. The difficulty, weirdly, is in the regularity. So one thing I brushed over earlier is that in all of this, in order to apply this, you need the regularity lemma to work. And C4 free graphs have this nice property that actually, if you take a C4 free graph, it can't contain any very dense spots. It can't be that most of the edges are contained in a small part. We don't know how to prove that for 6 cycles. We don't know how to rule out the possibility that there's lots of edges just bunched up in a small place. And if we could do that, then we could actually prove an analog of this for 7 cycles. And more generally, there's a question where if you ban 2K cycles, can you get counting for 2K plus 1 cycles? But the same problem holds. There's a problem with the regularity aspect. But if one could prove this, then it would generalize a lot of the things that we mentioned here. So I'll just give one example, but the one example I'll give is that you'd be able to count 3 uniform, sorry, you'd be able to say that a 3 uniform hypergraph on n vertices with girth greater than 7 has little o n to the 4/3 edges. Okay, so that's basically all I wanted to say, so I'll stop there.
Thank you very much, David, for a very interesting talk. So let's maybe those who can unmute themselves and give an applause for David. Are there any more questions for David?
Yes. So just a quick one. So you were so we used the girth 4 when we said, okay, we have root n degree, then the 2 neighborhood is of linear size.
Yeah.
But are we also implicitly using some sort of like Sidorenko style results?
Yeah, you sort of are. So in the regularity, you're using it. So so in proving that that you don't contain any dense spots, you have to use something like a Sidorenko type result. But it's a very simple, like Sidorenko for C4s is the basic, most simple version of Sidorenko. So it's just basically 2 applications of Cauchy-Schwarz. So yeah, there is something implicit, but it's not so hard.
So all of those should go through for C6 or C8 or anything.
Yeah,
like that.
all of that goes through, no problem. Okay. But the problem essentially is the scaling in the extremal number. So within the extremal number for C4, if you do a sort of unbalanced version, where you have m vertices, if you have a bipartite graph, m vertices on one side, n vertices on the other, contains no C4, what is the size of the thing? So if m is larger than, let's put it the other way, if n is larger than m, then the upper bound is m times square root n, which scales linearly in the size of the smaller side. For C6 or beyond, that doesn't happen. It's no longer linear in the scaling of one side. It actually, for C6, the extremal number in this unbalanced case is m to the 2/3, n to the 2/3. And it turns out that lack of, or that twist in the scaling kind of ruins the property of being able to show that you have no dense spots. It's still plausible that there are no dense spots, I think, but we don't know how to prove that. Or is it plausible? It might not be plausible, but it might be that you can at least show that there's lots of edges that don't contain any dense spots, or a subgraph with lots of edges not containing any dense spots.
Well, I think Maria probably wanted to ask a question, and also there is a question.
Yeah, if I may, so I was just wondering, coming back to this solutions, sets without non-trivial solutions to the certain linear equations. So you showed that you could basically go below the minimum, yeah, by some sub-polynomial term. So do you know something in general that you could never go down by actually polynomial, so into the alpha term? Is it, or do we believe in it?
Yeah, I don't actually know of any example like that, even for hypergraphs. And it may be that no such example exists. It might be that the compactness conjecture is sort of true, that it's true up to logs, say. So the natural place to start looking is actually for hypergraphs. So for hypergraphs, the standard example is you have two hypergraphs. One is basically a triangle of three uniform edges, and the other is just two edges sharing two vertices. And both of them on their own have extremal number around n squared, but together their extremal number is little o n squared. Yeah, I'm not sure. I think it's plausible to me at least that that might not hold, but I wouldn't be surprised either way.
All right, thank you.
There is also a question in the chat, David.
Let's have a look. Yeah, so in terms of the counting lemma, it doesn't involve any transference. It's essentially what I was talking about there, that the counting lemma in some sense is reasonably simple-minded, that you show that any vertex has a large 2 neighborhood, and then regularity tells you that that large 2 neighborhood will still contain edges. That is essentially the idea of the counting lemma. The removal lemma, on the other hand, does involve transference. So essentially what one does is you don't need the full regularity lemma. You need something called weak regularity to show that your dense graph has, your sparse graph has a dense model. And then you start with the condition that you have few copies of C5, say. Then you pass and you say that this dense graph also has few copies of C5, and that's actually the counting lemma that does that. And then when you're in the dense context, you apply the removal lemma in the dense context to get rid of the edges. And then whatever you did to get rid of the edges up there, you actually impersonate it down in the sparser graph. So within the removal lemma context, there is actually a transference principle happening.
Any more questions for David? Go ahead. Well, if not, then yeah, so let's thank David again and thank all the speakers of today's session of the conference. And we'll hopefully see each other tomorrow on the talk of Janos Pach and then the workshop by Sasha Palenski.